Hi guys, welcome back to my channel. As you know, today's Thursday and it's time for our beloved segment, Treasured Knowledge Thursdays. This is a weekly segment where I sit here and pretend like I know what I'm talking about, but in actuality, I don't. So the treasured knowledge that I'm here to share with you today is all about cryogenics. And no, it's not cryoelectronics, it's not cryobiology, and it's definitely not about cryonics. It's cryogenics. So what is cryogenics, I hear you asking? And don't worry, that's what I'm here to tell you about. Cryogenics is the study of extremely cold temperatures. In fact, the word cryogenic itself is derived from two Greek words, cryo, which means freezing, and genics, which means to produce. So based on this definition alone, you would assume that cryogenics include all temperatures below 0 degrees Celsius because that's the freezing point, right? But that's not the case. This is because a professor named Heike Kamerlingh-Onnes, yes, this guy, he defined cryogenics as a temperature that allows all permanent gases to turn into liquid. This means that it would only include temperatures below negative 183 degrees Celsius. But the thing that confuses most people today is the fact that the universal accepted scale for cryogenics is not negative 183 degrees Celsius. In fact, it's negative 150 degrees Celsius. There's really no reason for it to be negative 150 degrees Celsius. It's just the fact that numbers that can be divided into fives, tens, and hundreds are easier to do mathematical equations with. So when it comes to scale or measurement of cryogenic temperatures, there's one word that's going to be most often used, and that word is absolute zero. So according to the law of thermodynamics, there exists a temperature that cannot be surpassed. So meaning that there is a temperature out there that is the lowest temperature, so it can't go any lower. So as you may have already guessed, absolute zero cannot be achieved on Earth, and this is because there isn't enough sufficient power that can be produced in order to achieve such low temperature. But the good news is that we can achieve temperatures that are within a few billionth, yes, I said billionth, of such temperature. And this is what cryogenic is, basically. It is the closest we can get to absolute zero. So I'm assuming that you guys have never heard about the Kelvin scale before, which is totally normal. And this is why I have treasured knowledge Thursdays for you guys, remember? And so I'm going to tell you a little bit about the Kelvin scale. The Kelvin scale is actually much colder than the Celsius or Fahrenheit scale. And so 0 degrees Celsius, which is the freezing point here on Earth, is actually 273.15 degrees Kelvins. And this explains that the Kelvin temperature is actually just used to measure extremely cold things. So you can't really use, you can use it to measure warm things, but it's not sufficient. It's only used for cold things. When talking about the scale or measurement of cryogenic temperatures, one important instrument to be used is a thermometer. Now the regular mercury or alcohol thermometers that are most commonly used are useless when it comes to measuring cryogenic temperatures, and this is because they would freeze under such cold temperature. So what do we use, you ask? Well, simply we use a platinum-resistant thermometer that has a well-defined electrical resistance under different temperatures. So remember Heike Kamerlingh-Onnes? Yeah, him again. Remember his definition about cryogenics and how he said that cryogenics is the temperature in which permanent gases turn into liquid? This gave scientists an idea, and it is that to call cryogenics liquid air. This doesn't mean that the air we breathe in is liquid, it just means that permanent gases, as Heike Kamerlingh-Onnes said, turn into liquid. So now that we know what liquid air is, there are several different types of liquid air that we need to discuss. And here's the list. So we have hydrogen, oxygen, helium, nitrogen, liquid natural gases, and finally carbon dioxide that can be liquefied. So I'm going to run down each one of them, explain how each one of them is liquefied and what we use them for. The temperature in which hydrogen is liquefied in is negative 253 degrees Celsius, or to make it easier, 20 degrees Kelvin. And because of such a low temperature, hydrogen is actually said to be one of the most expensive permanent gases to liquefy. This is because a lower temperature means higher pressure, and higher pressure means much more expensive. So this is how it works. To produce a lower temperature, you have to pressurize the gas in a higher pressure power. So therefore, a higher power is used to generate that higher pressure. And it's also expensive because it's also contained in such high pressure. It's not only to produce in such high temperature, but you also have to contain the gas in such high temperature in order for it not to go back to its normal state, which is gas. So the next permanent gas in our list is oxygen, and as you know, oxygen is one of the most abundant gases in our atmosphere. Oxygen can actually liquefy in a relatively high temperature, which is negative 183 degrees Celsius, or in easier terms, 90.21 degrees Kelvin. So the next permanent gas on our list is helium, and helium is not just a cryogenic liquid when it's cooled down, but it's also considered to be a superconductor, and I'll explain what that means in a little bit. But to start with, helium liquefies in a temperature of negative 269 degrees Celsius, or in easier terms, 4.2 kelvins. Yes, that's very cold. And this is what allows helium to be a superconductor. Again, I'll come back to its meaning a little bit later. So helium is actually one of the most commonly used cryogenic liquids in cryogenic technology, and this is because of its very low temperature, and that's why they get a higher result from using helium than something like oxygen, which has a relatively high liquefaction temperature. So the next permanent gas on our list is nitrogen, and nitrogen liquefies at negative 195.8 degrees Celsius, or 77.36 degrees Kelvin. Nitrogen is mainly used as a semiconductor in industries, and it's used to make protective shields. And oil companies actually use highly pressurized nitrogen to induce the oil to crude to the top, and so that's how they would easily cultivate the oil. So the next permanent gas on our list is liquefied natural gas, or LNG for short. Liquefied natural gas is liquefied at a temperature of negative 160 degrees Celsius, or in easier terms, 117.2 degrees Kelvin. Liquefied natural gas is actually made out of mostly of methane. So methane makes up about 95% of liquefied natural gas. This is why liquefied natural gas is odorless, colorless, non-corrosive, and non-toxic. In fact, liquefied natural gas is also non-flammable. This is because it doesn't contain any oxygen, and therefore, if it doesn't contain any oxygen, it cannot oxidize and in turn cannot create any flames or fire. So the final permanent gas we're discussing today is carbon dioxide. Carbon dioxide is actually not considered a cryogenic temperature. This is because carbon dioxide liquefies at a temperature higher than negative 150 degrees Celsius, which is the base minimum for cryogenic temperatures. In fact, carbon dioxide liquefies at negative 78.5 degrees Celsius and 194.7 degrees Kelvin. You're probably thinking, why should we know about this if it's not even considered a cryogenic? Why is this part of your topic? And the easy answer is because I have to discuss the phenomena of dry ice, and the easiest way to achieve dry ice is by liquefying and then freezing carbon dioxide. So remember earlier when I told you that helium is a superconductor? And by this I meant that helium has zero electrical resistance when cooled down to cryogenic temperatures. But this is not only true about helium. This can also apply to many other elements that have low resistance to electricity to begin with, but when cooled down, they have absolute zero resistance to electricity. So we have discussed the different types of liquid air, but we haven't discussed how liquid air itself is actually achieved. And by this I mean the process that takes a gas and turns it into a liquid. So how scientists do this nowadays is that they would take a certain amount of gas and compress it into a pressurized tank, and heat it up and then let it cool down into room temperature and then cool it down further while it's in the pressurized tank until it reaches a temperature where it would liquefy. So now that we know how to achieve liquid air, we also need to know how to contain it. This is a fairly simple task because specialized containers such as the Dayware flask, this one right here, are used to contain it. Dayware flask is 6 feet tall and 3 feet in diameters, and it's used to contain liquefied natural gases. So the uses of cryogenic technology vary. For example, in the field of biology, one of the most fascinating uses of cryogenic technology is in cryogenic surgery. It's not really surgery in the traditional way where you cut into someone's skin. In fact, it only exposes a certain part of the skin or a certain part of the tissues that are near the skin to extremely cold temperatures, and this can help with things like cancer or even just infections on the skin. So one of the many things that came about after studying superconductors is MRI. Yeah, this MRI right here. And chances are that you or someone you know have used an MRI when going to the doctor's office or a hospital, most likely.